This is the first of two revision videos looking at the vector work of the FM1 unit. In this revision video we will be looking at the vector and Cartesian equations of a straight line in 3 dimensions. We will be looking at how to calculate the scalar product and how to use it to find the angle between two lines. We'll also use the scalar product to check whether two vectors are perpendicular. And we will be looking at how to calculate the perpendicular distance between two lines and also the distance from a point to a line. So now let's have a look at the key facts for this section of work. The first one is that we should recognize the two equations of a line in 3 dimensions. If we have a line which passes through the point A and which has a direction vector of B, then we should know that the equation of that line is R equals A plus T times B, where R is the position vector of a general point on the line. A is the position vector of the known point on the line, which we are calling the point A with coordinates A1, A2 and A3. And T is a scalar, that is just a normal number, and B is a known direction vector for the line. Direction vector for the line is simply a vector that runs along the line. If we move into coordinates and we call our general point on the line the point xyz, then we have the equation R equals A plus TB becomes xyz equals A1, A2, A3, that's the position vector of A, plus T times B1, B2, B3, and B1, B2, B3 is the direction vector of the line. That vector equation that we've got can be written as 3 separate equations. We can write it as x equals A1 plus T times B1, y equals A2 plus T times B2, and z equals A3 plus T times B3. If we rearrange each of those 3 formulae to make T the subject, we obtain T equals x minus A1 divided by B1, T equals y minus A2 divided by B2, and T equals z minus A3 divided by B3. And this gives us the Cartesian equation for this line, which is that x minus A1 divided by B1 must take the same value as y minus A2 divided by B2, which must take the same value as z minus A3 divided by B3. So we've got the Cartesian format for the equation of a line, and we have the vector format for the equation of a line. If we have 2 lines, then it's possible that the 2 lines could be parallel, or they could intersect, or they may not be parallel and they may not intersect, in which case we say that they are skew lines. So, given the 2 lines, the first thing to do is to decide whether the 2 lines are parallel or not, and we do that by looking at the 2 direction vectors. If the direction vector of the second line is a multiple of the direction vector of the first line, then the lines are parallel, in which case we just need to consider whether the known point on the second line lies on the first line as well. So if the point C with coordinates C1, C2 and C3 all lies on L1 as well as on L2, then the 2 lines are going to be identical. If C doesn't lie on L1, then the 2 lines are distinct, but they're also parallel, in which case there are no points of intersection. If the two lines are not parallel, then the strategy is to find values of s and t so that two coordinates of L1 agree with the corresponding coordinates of L2. With these values of s and t, we then look at the third coordinate of each of the two lines. If they agree, then the lines intersect, and if they don't agree, the two lines must be skew. Moving on to the scalar product. The scalar product of two vectors is usually written as a dot b. So we've got a dot b is the length of the first vector times by the length of the second vector times by the cosine of the angle between the two vectors. If we know the two vectors in their coordinate forms, then it's very easy to work out a dot b. It's simply the result of multiplying a1 times b1 plus a2 times b2 plus a3 times b3. If a and b are non-zero vectors, then a and b are perpendicular if and only if a dot b is equal to 0. That's because of the cos theta term inside the definition of the scalar product. We can use the scalar product to do several things, and in this video we'll be reminding ourselves how to find the angle between two vectors, the angle between two lines, and also how to find a vector which is perpendicular to each of two non-parallel vectors. We've also got to look at distances in 3 dimensions. The first one is the Pythagorean result for the distance between 2 points, which you'll certainly have met earlier in your studies. The perpendicular distance of a point Q from the line r equals a plus tb can be considered in 2 different ways. Possibly the easiest way is to start by drawing yourself a diagram, and from the diagram there we're looking to find the perpendicular distance of Q from the line, so that's the distance d on the diagram, and we can use the scalar product to find the acute angle between AQ and the direction vector of the line. Having found that acute angle theta, then the required distance d is simply AQ, the length of AQ, times by sine theta. The perpendicular distance between two non-parallel lines is given by a rather complicated formula, which is it's the modulus of c minus a dot n, so it's a scalar product of c minus a with n, divided by the size of the vector n. Now that formula is quite difficult to remember, but fortunately the formula is inside the formula booklet that you'll be given in your examination. So now let's move on and start looking at some examples. So in the first example we've got the points A and B are 2 minus 2, 1 and 1 minus 4, 8. We've got to find the vector equation of the line L, of the line AB first of all. We then have a second line L, which has got Cartesian equation x plus 12 over minus 2 equals y over 2 equals z minus 34. We have to find the angle between the two lines, and we have to determine whether or not the two lines intersect, and if they do intersect, determine their point of intersection. So a diagram's often a good idea in vector questions. So there's my very simple diagram representing the line AB. The direction vector for the line will simply be the vector joining A to B, so that's the vector -1, -2, 7. The equation of the line now is given by R equals 2 minus 2, 1. That's the position vector of the point A, plus a scalar, in this case we're using S, times the direction vector for the line, which is the vector -1, -2, 7. Moving on to part B, the Cartesian equation that we've got there, x plus 12 over -2 equals y over 2 equals z minus 34, can be rewritten as x minus -12 over -2 equals y minus 0 over 2 equals z minus 34 over 1, which is exactly the format to tell us that the vector equation of the line L is r equals -12, 0, 34 plus t times -2, 2, 1. So to find the angle between the two lines, well, the angle between two lines is defined to be the angle between their two direction vectors. So we're trying to find the angle between the vector -1, -2, 7, that's the direction vector of AB, and the vector -2, 2, 1, which is the direction vector of the line L. So we're going to use the scalar product, and we're going to find the scalar product of -1, -2, 7 with -2, 2, 1. So it's very easy, first of all, to calculate the value of that scalar product. -1 times -2 plus -2 times 2 plus 7 times 1 gives me 2 plus -4 plus 7, which gives us 5. On the other hand, we know that the scalar product is the length of the first vector times by the length of the second vector times cos theta, where theta is the angle between the two vectors. So that simplifies to square root of 54 times by square root of 9 times by cos theta, and square root of 54 is 3 root 6. Square root of 9 is 3 times cos theta. So we've got root 54 times root 9 times cos theta simplifies to 9 root 6 cos theta. So putting our two pieces of information together, we know that 5 must be the value of 9 root 6 cos theta. In other words, cos theta is 5 divided by 9 root 6, which tells me that theta is 76.89 degrees. So we've now found that the angle between these two lines is 76.89 degrees. So finally, we need to have a look at whether these two lines intersect or not. The first thing to do is simply to observe that the lines are not parallel lines, because -2, 2, 1 is not a multiple of -1, -2, 7. So now let's try and find values s and t so that the x-coordinates of the first line and the x-coordinate of the second line agree, and that the y-coordinate of the first line and the y-coordinate of the second line agree. So if the x-coordinates are going to agree, we've got to have 2 minus s equaling -12 minus 2t, which we can rewrite as being 14 equals s minus 2t. And if the y coordinates of the two lines are going to agree, we've got to have -2 minus 2s equals 2t. In other words, 2s plus 2t must equal -2. We've got a pair of simultaneous equations, and for those simultaneous equations we obtain s equals 4 and t must equal -5. Now we must now use the third coordinate, in this case the z coordinate, to determine whether or not the lines are intersecting lines. So if s is 4, the z coordinate of the first line is 1 plus 7s, so that's 1 plus 4 times s, which is 29. On the other hand, if t is -5, then the z coordinate of the second line is 34 plus t, which is 34 plus -5, which also gives me 29. So the fact that z1 is the same as z2 tells me that the lines intersect, and the point of intersection can be found by substituting s equals 4 into the first line. And if we put s equals 4 into the first line, the x-coordinate is 2 plus 4 times -1, so that's -2. The y-coordinate is -2 plus 4 times -2, so that's -10. And the z-coordinate is 1 plus 7 times 4, which is 29. So the point of intersection is -2, -10, 29. So let's move now to our next example. We have two vectors b and d. b is the vector 3i plus 2j minus 5k, where remember I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. We've also got d is I minus j plus 3k. And the first task is to find a vector which is perpendicular to both b and d. Let's suppose that n, the vector pqr, is perpendicular to both b and d. The fact that n is perpendicular to b means that the scalar product of n and b must equal 0. So we've got 3, 2 minus 5 dot pqr must equal 0. In other words, 3p plus 2q minus 5r equals 0. Similarly, n must be perpendicular to d. So that gives me the scalar product of 1 minus 1, 3 with pqr must equal 0. So we've got p minus q plus 3r equals 0. I'll call these two equations 1 and 2, and you'll notice that we've got two equations but three unknowns. So in this case, the best that we can do is we can try and solve the equations to find two of the variables in terms of the third variable. So looking at equation 2 to begin with, we can say that we have p is equal to q minus 3r. Substitute that into equation 1. We've got 3 lots of q minus 3r plus 2q minus 5r equals 0. Simplify that, we've got 5q minus 14r equals 0. That tells me that q must be 14 over 5 times r. And if we substitute that back, we've got p then is 14 over 5r, take away 3r, in other words p is minus a fifth r. Now we can choose the value of r to be whatever we like. I'm going to choose r equals 5, simply because it will remove all the fractions. So that will give me p equals minus 1 and q equals 14. So the normal the vector n, which is perpendicular to b and d, is minus 1, 14, 5. That answer is not unique. We could have double that vector, so we could have the vector -2, 28, 10. Would also be perpendicular to both B and D. All we're looking for, though, is a single vector that is perpendicular to B and D. So any multiple of that vector n would in fact do. Moving to the second bit of the question, we have two lines. And the important thing to notice here is that the direction vector of the first line is the vector B, and the direction vector of the second line is the vector D. We're looking for the perpendicular distance between the two lines. We have the result from the formula booklet that we commented on earlier. So for the first line, the position vector of the point that we know the first line goes through is 5, 1, 0. That's the vector A. The vector B we already know is 3, 2, minus 5. That's the direction vector for the first line. The position vector of the point that the second line goes through is the vector C, which is 7, minus 4, 3. And the direction vector for the second line is the vector D, which we know is 1, minus 1, 3. The vector C minus A can be worked out easily. And we also know from part A that our vector n, that's the vector which is perpendicular to both B and D, is the vector -1, 14, 5. The length of that vector can be calculated by finding the square root of -1 squared plus 14 squared plus 5 squared, which is the square root of 222. So the perpendicular distance can be found by working out the modulus of the scalar product of C minus A with n divided by the length of n. The scalar product can be calculated as -2 add -70 add 15, which gives me -57. So the perpendicular distance is the modulus of -57, i.e. 57, divided by the square root of 222. So that's approximately 3.83. Finally, we move on to part C. Find the acute angle between the two lines. We know the angle between two lines can be found using the scalar product of the two direction vectors. So the two direction vectors are 3, 2, minus 5 and 1, minus 1, 3. If we evaluate the scalar product in the normal fashion, we've got 3 add -2 add -15. And we also know, though, that the scalar product is the length of the first vector times the length of the second vector times the cos of the angle in between the two vectors. So we have -14 equals the root of 38 times the root of 11 times cos theta. So cos theta is -14 divided by root 38 root 11, which tells me the angle between the two vectors is 133.2 degrees. The angle between the two lines is 133.2 degrees. But this is clearly the obtuse angle between the two lines. So the acute angle between the two lines will be 180 minus 133.2. In other words, 46.8 degrees. And finally, we move on to our final example, but we're going to have a look at two possible ways of solving this question. So we want to find the perpendicular distance of the point 12 minus 9 minus 3 from the line through the points 1, 5, 3 and 5, 1, minus 3. Okay, well, we'll start off with a sketch diagram. So we've got the points A and B giving me the line, and we can straight away work out the direction vector for the line as 4, minus 4, minus 6. Now we want to calculate the perpendicular distance D, and from the triangle that we've got drawn we can see that D is equal to the length of AC, which is the hypotenuse of the triangle, times sine theta, where theta is the acute angle between the vector A to C and the direction vector of the line. So we've got a little bit of scalar product work to do first of all. We've got A to C is the vector 11 minus 14, 6. So 11 minus 14 minus 6. So we've got the scalar product of 11 minus 14 minus 6 together with the direction vector 4 minus 4 minus 6. Numerically, that gives me 44 plus 56 plus 36 must equal the length of A to C times by the length of the direction vector times the cos of the angle between the two vectors. So simplifying that, we've got 136 equals root of 353 times the root of 68 times cos theta. So we've got cos theta equals 136 divided by root of 353 root 68. That gives me that theta must be 28.62 degrees. So the length that we're trying to find, D, is AC sine theta. We've already determined that AC has a length of 353, so root of 353. So we've got the root of 353 times the sine of 28.62 degrees, and that's giving me a distance, a perpendicular distance of C from the line of 9 units. Now there's a second way through this problem. Okay, again we've got a diagram to start off. The second solution takes into account, first of all, the fact that the equation of the line AB is going to be R equals 153 plus T times 4 minus 4 minus 6. And we are going to consider the point P on the line, which is where the perpendicular from C meets the line. Now P is on the line, so there must be a value T such that the coordinates of P are 1 plus 4t, 5 minus 4t, 3 minus 6t. We know that the line P to C is perpendicular to the line AB. In other words, the vector P to C must be perpendicular to the vector 4 minus 4 minus 6. Well, the vector from P to C, if I start at 1 plus 4t and move to 12, that in the x direction is a movement of 11 minus 4t. If I start at 5 minus 4t and move to minus 9 in the y direction, then that is a movement of minus 14 plus 4t. And if I start at 3 minus 6t and move to minus 3, then that is a movement of minus 6 plus 6t. So the vector P to C is the vector 11 minus 4t, minus 14 plus 4t, minus 6 plus 6t. And the scalar product of that with 4 minus 4, 6 must equal 0, because we know that P to C is perpendicular to 4 minus 4, 6. So if we evaluate the scalar product, we've got 4 times 11 minus 4t, in other words 44 minus 16t. We've then got minus 14 plus 4t times minus 4, so that's plus 56 minus 16t. And then finally, we've got minus 6 plus 6t times by minus 6, which gives me 36 minus 36t. Add those lot up together, we've got to have 0. Simplify, we've got 136 minus 68t equals 0, which tells me that t is 2. Now if t is 2, we know the coordinates of the point P are 9, minus 3, minus 9. And the vector P to C is going to be 3, minus 6, 6. So the length P to C is 9 units exactly. Same answer we've got before, except this one actually is exact, whereas the previous one was to 3 significant figures.